Okay. Now we finally learned how to differentiate, so we're all excited. Let's talk about higher order differentiation. Basically a fancy name for second derivatives, third derivatives, etc. Right, we call that higher order. If we're taking the second derivative, it's a higher order derivative. That's what it's called. Okay. So again, done as you would expect. Take a derivative, then take it again. Example. The second derivative with respect to x. So this means differentiate by with respect to x, and then again differentiate the result with respect to x. And if you're wondering, yes, you can differentiate with respect to different variables. So you could take derivative with respect to x, then differentiate with respect to y. Or with respect to y, then differentiate with respect to x. Right? You can mix and match here. So let me explain some more notation. How do I sort of do this? Let's say f of x, y is a function in second order. You can take fx and then you differentiate with respect to x again, right? Or you can take fy and differentiate with respect to y again, then you can take fx, then differentiate with respect to y, or you can take fy, then differentiate with respect to x, right? Right? So this, if you're writing this as notation, you just write fxx, right? Here you'd write fyy, here you'd write fxy, here you'd write fyx, right? So this means differentiate with respect to x first, then differentiate with respect to x second, right? It goes from order left to right. Right? So the first guy is here, the next guy is down. So this is similar. Here it means you differentiate with respect to x first, then differentiate with respect to y second, right? And so on and so forth. Right? So the notation is read from left to right. Now, partially the confusing thing about this is when you're doing it the other way, the notation is sort of read backwards, right? So remember, fx is equal to partial of f with respect to x. Now the second derivative says you're actually going to take your result, right? And then you're going to take the derivative of the result. Well, that means on top you have d squared f and dx squared. Right? Notice though, if we had something like fx, and now I want to find fxy, What that means is I had this guy, fx, and then I differentiated with respect to y. And so this would be d squared f, and this would be dy dx, even though the x is first and this comes second. Right? Because this notation, you tack things on the left, you read from right to left. This is the first one you differentiated with respect to. This is the second one, the third, the fourth, goes out to the left. Well, these guys, you tack on subscripts to the right. So they're sort of read in opposite directions, right? So this means take the differentiator with x first, then with respect to y. This also means take the derivative of x first, then with respect to y. You'll get used to it when you start doing a lot of problems, but just notice that they are read in opposite directions, just by how the notations function. The subscripts are always attached to the right, so you'd read from left to right, but the d's are always attached on the left, so you'd read from right to left. Okay? Just something to be aware of. Yes.
You can't make it d squared yx in the bottom. It has to stay in that form.
No, it's d, right. This guy is like dx all squared. That's how you think. Yeah. No. Like your dy is one thing. It's just, you can't really fuck this off. Okay. Example. Find the second partial. Maybe I should make that note. The subscript notation read from right to right. Again, this is a D notation. This is called the Leibniz notation. That's like in is read from right to left. In terms of which variable you differentiate first. Okay? So how do you find the second partial? Well, we first have to find the first partials, right? Which, this was the same one that we had before. So fx, we find that, we would get 6x squared y plus 3 cubed. And that y, that would be
6x, no, just 2x.
Now after that, we can find fxx, which means you take the derivative with respect to x, then you find the derivative with respect to x again. Right? So we're looking at this one, I'm going to find the derivative with respect to x again. So this would be 6 times 12xy, 0. Right? I can find fyy, which means I take the derivative of y, then I find the derivative of that with respect to y again. So I'm looking at this guy, find the derivative with respect to y.
18xy
Isn't that 0?
Yeah, but it's
y squared.
Right, this is 0.
Oh.
Okay, now let's find the other one. What if I say partial with respect to xy, right? This means I look at the partial with respect to x, then take the partial with respect to y. So I'm looking at this guy, and now I'm going to differentiate with respect to y. Right?
Minus 6x squared plus 9y.
Minus
Squared.
6x squared plus
9y
9y
squared.
squared. Right? So this is differentiate fx with respect to y. Now, if I look at the other way, right, derivative of yx,
So then it would be
look at this one, and I want to differentiate with respect to x now.
Negative 6x squared.
Minus 6x squared plus, remember I differentiated this with respect to x, so I get 9y squared, and then that's 0. And so this is differentiate fy with respect to x. It's not a coincidence that the derivative of x with respect to y is equal to the derivative of y with respect to x. In fact, here we can know why. There's something called Clairaut's theorem, right? I don't know, someone probably was thinking about this when I was writing these down. Why do you have to do yx and then xy? Aren't they the same? Well, in this case, they're the same, but they're not always the same. Let me make sure I spell this guy's name right. There's something called Clairaut's theorem, right? And it tells you that you can actually switch the partials and it won't make a difference in a particular case, right? Suppose f is defined on a set E and its partials then if partial with respect to x and partial with respect to y are continuous, then fxy equals fyx. Does the original function have to be continuous? No, if these guys are continuous. So as long as you take the second order partials and you get continuous, they will necessarily be the same. In this case, our second order partials are polynomials, which are continuous everywhere. And so no matter which way you do it, you'll get the same answer. Right? It's not always true. It's true in the case where they are continuous. So there is actually a theorem for that. That's nice. Clairaut's theorem really talks about a derivative at a point, but see another example. F of x, y, z. And of course, everything in second orders generate naturally to higher orders than that. F of x, y, z equals y e to the x plus x and z. Find f, z, z, x, and f, x, x, z. You guys think you have the answer? You try that. Okay, let us start this one. How do we get to that then?
Take the derivative with respect to z, and then with respect to z, and then with respect to x.
Right. Find the partial respect to z first, then find partial respect to z again, then find partial respect to x. So first we're going to find xz. That's going to be equal to
1 over z.
X over z.
x over z.
So that's right.
So if we have xz, z is the next thing we'd have to find, which is
Negative x over z squared.
and so if I take f, z, z, x,
1 over z squared. Negative 1 over z squared.
okay. So what if I want to find this guy? Similarly, x first, then x second, then z third. Derivative with respect to x.
Y e to the x plus ln z.
Derivative with respect to x again, give us fxx.
Y times e to the x.
Right, because there's no x in that, so it's 0. And then I can do fx, x, z, which is
0.
Moving on to 11.4. 100 things. The goal here is given a surface, how do we find a tangent plane to that surface? Just like if we were given a curve, how do we find a tangent line to the curve? Same idea, more dimensions. Right? So let's see what I said about that. I gave it. Let me write that. Anyway. Is the best approximation we have. So this is similar to what we saw before. They're complete. So you're at the point AB, then you have the tangent lines in the x and the y direction. The plane that contains these lines is called the tangent plane.
Thank you.
By illustration, when I say vector approximation, we mean you zoom in the tangent plane and the surface itself are very close together, right? The more you zoom in, the less difference you can tell between the surface itself and the tangent plane. So it's a very good approximation. And I don't know if back in Calc 2, you remember you did the topic called linear approximation, right? It's sort of where evaluating the function at certain values was really difficult, but what you could do is you could just do a linear approximation where you sort of transform the function into a line, right? What you really did was the tangent line, right? You had some random curve that was really hard to compute values, but you want to know what's the value around here. And what you do is you create a tangent line there, right? And then you assume that the value of the function is the same as the value of the tangent line, because if you zoom in far enough, right, it's pretty much the same. And so that's going to be the idea. We're actually going to be doing that with tangent planes. That's one of their uses, to approximate weird surfaces. And as long as we can differentiate the partial derivatives, we will be able to do this. Right? That's sort of what happened back in the. At the end of the day, that's what a function being differentiable means. It means you could approximate it with a tangent line, right? The reason why sharp corners you can't differentiate them is because, how can you draw a tangent line to this thing? Right? You can have tons of tangent touching at one point, and the distance between them can be huge, right? That's why sharp corners you couldn't differentiate. The difference quotient breaks up. But smooth curves you can, right? So once you can find a derivative or a partial derivative, we'll be able to do this. And now we're going to figure out the formulas, how we can do it. So. The question is, how do we get the equation of a tangent plane? Well, first of all, it's a plane. Just like a tangent line is just a line. It has a certain form. So we know it has the form right? Because it's a plane. Right? Now we can actually solve for this in a weird way. We can say solve for z minus z0, assuming c is not 0. And we'd have minus a over c minus b over c. Okay? So you can have that, right? Now, look at the point x0, y0, z0, and fix y equals y0, right? In other words, let y be a constant. What do we get if y is a constant, in particular that constant?
Z equals x.
Then you have z minus z0 is equal to minus a over c times x minus x0, right? With your y fixed at this constant. Now what is this? This is just a straight line in the xz plane, right? And z is now a function of x and a constant, right? Which means that line, we can actually find its slope, right? In fact, we know what the slope is. It's minus a over c. But what is this gives us the slope? The derivative gives us the slope of a tangent line. So it's going to be the derivative. And since it's fixed with a constant y, it must be the derivative with respect to x. i.e. your minus a over c has to be the partial of f with respect to xy at the point. Similarly, minus b over c has to be the partial with respect to y at the point. So the tangent plane to z equals f of x not f of xy at point x naught y naught z naught is basically, you slice things, you look at the tangent line, and you sort of that, oh, the slope in the x direction has to be that. And you can sort of replace it. Right? That actually gives you the equation of a tangent plane to a surface. You don't have to know how to derive this, just show it. You have to remember that, right? If you're finding the tangent lines, that's the form. If you're finding tangent line to something that looks like this. I'll give you a slightly more general form later, but for now, that's what you have to know. The derivation makes it look scary, but it's not that scary, so let's do an example. So basically, the picture here, and I guess next week when we do MATLAB, you'll be able to see these things more clearly. What does that look like?
It's a parabola. Long as
Took too long. Okay, so this is a paraboloid, right? Now there's a point where x equals 1, y equals 1, and z equals 2, right? At that point on the paraboloid, I want to find the tangent plane. Alright, so I'm given a surface, in this case it's a paraboloid. At this point, 1, 1, 2, find the plane that touches only at that point, 1, 1, 2. And that's the formula. So it means we're going to need to find the first partial derivatives, right? So if z is equal to f of xy, then fx would be equal to, in this case,
x.
2x, which means if I take the partial and I evaluate it at the point 1, 1, 2, what is the answer? Fy is
Or 2y.
2y, which means if I evaluate that at the point 1, 1, 2, what do I get? 2. Therefore, the tangent plane z minus 2 equals 2 x minus 1 plus 2 where this 2 goes here, and that 2 goes there. And this is the point Z0, this is the point X0, this is the point Y0. Right? But that would be the equation of the tangent. So it's not so bad. You're given a function, find the partials, evaluate at the point, put it here and here. Yep, that's sorted. That's it. That's the tangent plane. Right? This is the plane that will touch that surface at that point. Yep, that's it. Looks very anticlimactic. That's basically where we headed. And we can also do, the tangent plane actually gives us the equation for a linear approximation, just like the tangent line does. Which means we can sort of evaluate points on the surface by knowing what the points are on the tangent plane. You can get a very good approximation, depending on how the surface looks. Because again, this is a linear function. Plugging in values into this and solving for it, easy, right? But your original function might look really nasty. So working with this guy in general is easier than working with that guy. So we actually use tangent planes to do that. It's still called linear approximation. For example, suppose that is a function for which AB, fx of AB, y of AB, then this function, L of xy, equals f of AB plus is called linearization of f at AB. Right, pretty much you saw for z in the original formula. It's a very important function because you can use it to approximate it, and approximation that f of xy is roughly f of AB plus fx. This is fx evaluated at AB. Eventually I'll get too tired to write the coordinate, but it should be obvious. Plus fy of y minus b is called a linear approximation. closer your point is to the values that you know, the better the approximation is. So let's do an example. Same function we had before. Okay, how do you find the linearization? Remember, L of x, y is equal to f of AB plus x at AB, x minus a plus y at AB, and minus b. So let's find the partials first. Fx we knew was 2x. This means fx at AB is just 2a. Y we know is 2y, so at y at AB is just 2b. F of AB is just a squared plus b squared. So okay, that's the linearization. Now, to approximate. At 0.99, 1.1, use so remember xy is the actual point. AB is a nice point that's close to xy that you think you know, right? This is just like calc2, so it's the same thing. So this would be 1, 1, right? So xy, actual points, you want to approximate f at, this is a nice point, close to xy, that you know f of x of y at. So in this case, f of 0.99, comma 1.1 is going to be approximately equal to that formula I had over there. Going to be close to f of 1, 1 plus fx at 1, 1, x minus 1 plus fy at 1, 1, 1 minus 1. Or just place a and b with 1 and 1. So this is going to be 2 plus, plug into here, a equals 1. 2, the x, I would make it 0.99. Plus 2 times 1.1. 0.99 minus 1.
Negative.
Point oh one.
No one.
Minus 0.01 plus 2 times 0.1. So that's just 2 minus 0.02 plus 0.2. Yeah?
I have a question. Shouldn't that be on the top line 2b times y minus b?
This is y, yes. Okay, so you have 2.2 minus 0.02, what do you get? Huh? 2.18, you said?
Yes.
Okay. Right, so that's your approximation. Now, that should be close to the value you get if you took 0.99 squared and then added it to 1.1 squared. Right? As you can see, 0.99 squared, even for a simple function like this, 0.99 squared, doing it by hand or anything like that, it's actually pretty annoying. This was a much easier computation. Similar problem here that you could get on an exam or something. Can give you a function and say approximate at this point. First thing would be to find fx. First, you'd state yourself. Use xy equals 1.1, 0.9, and AB equals 1 and 1 would again be a nice choice. So fx would be, in this case, what's fx?
3x squared y, 2x, no, y squared. That's it.
So fx at 1, 1 is
3, 1,
4. Right? Now if I say fy, that would be
x cubed, 2xy,
and so if I say fy at 1, 1,
3,
And if I take f at 1, 1, this means that f of 1.1, 0.9 is approximately equal to f at 1, 1 plus the partial with respect to x at 1, 1, x minus 1 plus partial with respect to y at 1, 1, y minus 1, which is going to be 4 plus 4 times 1.1 minus 1 plus 3 times 0.9 minus 1. This is 4 plus 1.1 minus 1 is 0.1, so that's 0.4 plus 0.9 minus 1 is minus 0.1. So it's minus 0.3. So that would give you what? 3.9?
4.1.
Yes, plus minus. So it's 4.1.
Shouldn't this be 1.82?
What, you mean over here?
Yeah.
No.
2 minus 0.02 plus
No.
0.2.
No, because it's 2 plus 0.2.
Is 2.2.
2.2,
Minus?
which you can think of as 2.20.
Yeah.
And then you minus 2 from that. 20 minus
Okay.
2 is 18. Yep. It's lining up the zero square.
Yeah.
But yeah, that's your approximation here, which I'd much rather evaluate it in this function than to be cubing 1.1 and squaring 0.9, multiplying these and adding 2. Right? This was a lot easier to plug into here. Now for these, you're going to say, well, we're in the age of computers, let's have the computer do it. But remember, we're doing very simple functions here. In general, in practice, the kind of functions that someone would deal with when you're running on computers would be really complex. And even the computers might take a while, wasting computing time, wasting power, wasting, you know, a lot of CPU power, computing all these functions, when really all you have to do is just use calculus, approximate with a much nicer function. If you're close enough, everything works out nicely. Your computer works a lot easier, a lot faster. Things move a lot faster anyway. So whether you're doing by hand or computer, this is important. Because there are some functions where the more times you're iterating their values, the longer it would take to compute. Right? Never mind. Those of you who do computer science will talk about that. Let's see. Definition. Y is we have an hour left. Differentiable at a b. This is the easy. There's another definition again that I'm skipping with epsilons. In the summer, I just think it's too much to go through.
No, you should go through it.
Differentiable at a b if yeah. Now put it on a test and everyone. If fx and fy exist at a b and are continuous. Right, so that's a simple criterion to check. We say something is differentiable if both partials exist and they're continuous there. Differentials, which is in general, I think differentials are pointless. They're really linear approximations, but it's just a different notation. So basically, if you see something like x minus the x naught, you think of that as dx, right? Meaning the change in x. Or y minus y0 dy, which you think of as change in y. Your z minus z0 is of course dz, which is a change in z.
Are these, should these be like real equal signs or approximately equal signs?
Technically, they're approximate equal signs.
Oh.
If you're very close to AB, that's what they're. And so, if you have z minus z0 is equal to fx, x minus x0 plus fy minus y0, you can write this as dz equals fx times dx plus fy times dy. This guy in this case is called the total derivative. That's really just a linear approximation. Hence, you could say something like f of xy is approximately equal to where these guys are evaluated at KB. Total derivative. This is total differential. Total differential. We probably box this because they'll ask for it specifically. This will be the last example. It's going to be the last example. These are straightforward computation, you're just following that formula. Let's do that. In A, the total differential of this is just going to be, you're finding dz, which you know is the partial with respect to x of this times dx plus the partial with respect to y times dy. So what's the partial with respect to x of this?
2 sine
2 sine y.
minus 6x y squared.
Take all of that times dx plus partial with respect to y.
2x cosine y minus 6x squared y.
Take all that times dy. That's it. That's the total differential. B. Here we want to find dw. Which, by the way, you should notice that this is zx times dx plus zy times dy. That's what all of this is. dw is going to be equal to w with respect to x times dx plus w with respect to y times dy plus w with respect to z times dz. W with respect to x is 2x. W with respect to y is just 2y. W with respect to z is just 2z. That's it. That's called the total differential. And you can sort of think of it, the differential as giving you the error in something, right? The error in measuring z, right? This is the change in z, right? It's how much z changes from what its original value was. So you can pretend that you gave these dimensions to a guy to make a box, but he's like farsighted, and he cuts the box and he cuts the lengths of the pieces in the wrong order. You can see, and it could be off by as much as 0.01 centimeter. And you're a stickler for this. You want to figure out, well, how much could he be wrong by? Right? So, right, these are the dimensions you wanted, the original dimensions, but they could actually be off by 0.1. So instead of 50 centimeters, you could have 50.01 or maybe 49.99. Right? You have this error there. Right? What's the maximum error that you can have? You can actually use differentials to figure this out. So if we let V equal the volume of the box, then V would be equal to, give me a formula. X, Y, Z. So the change in V is the error is actually the total differential, the dV. And dV is equal to dx times dx plus dy times dy plus dz times dz. And we want to evaluate at the nice points, 50, 20, 15. So basically here, dV is going to be equal to partial with respect to x of that. That's just yz. And you want to evaluate that at 50, 20, 15 times dx plus, now you have x, z evaluated at 50, 20, 15 times dy plus xy evaluated at 50, 20, 15 times dz. So our y was 20, z was 15. The change in x could be as much as 0.1, right? It's actually the change for all of them. Plus x was 50, Z was 15. The change in Y is also 0.1. That could be the maximum error. X is 50. Y is 20. Change in Z is that. So you could actually have a change in volume of that many centimeters cubed.
Where'd you get 0.1 from?
The error. Right? It means that X could be off by
Okay.
0.01 on either side. So the change in X is
0.01 or 0.1?
0.01. They should all be 0. And so what's that? Twenty times 15?
300.
So this is 300 plus 50 times 15?
750.
750 plus
100.
1,000.
You forgot
That's
to
a
multiply.
a little over 100. So you can kill these guys.
That made it easier.
So that would be what?
205.
205 over 10. So,
It's 20 point.
and that's centimeter cubed, and so this is 20.5 cubic centimeters. You can be off by that much volume. Which, it might seem like a lot, but what's the relative error? How do we find relative error? Divided by the total. Right? So, relative error equals the error divided by the actual value. So the error here was 20.5. What is the actual volume? It's 20 times 50 times 15. What was that? I think I read that one. It was actually 0.14%. So 20 cubic centimeters sound like a lot, but in terms of the actual box, you're only off by 0.14%. So it depends on how OCD you are and how much you want to kill this guy for being far-sighted. And that ends that. So I guess 11.3 and 4 are due tomorrow.